Hey everyone, in this video we will be discussing on how to solve a partial differential equation, Laplace equation with Dirichlet boundary conditions in a rectangular region. First of all, let me explain what each of these terms mean. Partial differential equation means we have an unknown function, in this case u, that is function of two independent variables x and y. That's why we call it partial differential equation as opposed to ordinary. It's a Laplace equation because we have del squared of u equals to 0, and del squared simply means the second derivative of that unknown function with respect to x plus the second derivative of u with respect to y equals to 0. This is an important equation for electromagnetics if U is voltage, for heat transfer if U is temperature field, and for mass transfer if U represents concentration. We have Dirichlet boundary conditions if the boundaries have some equations in terms of the value of U at the boundaries. If we had Newman boundary condition, it would have had a partial derivative of u at the boundary. So in this case, as you can see, we have some information for the value of u at the borders. So we are dealing with Dirichlet boundary conditions. In the next video, I will give another example with Newman boundary conditions. To solve these types of PDEs, we could use Fourier transform, Laplace transform, and other ways. But for this video, I will be focusing on using separation of variables. So this is a well-known technique to solve PDE problems. And what that means is we assume that this unknown function u is a product of a function that is purely in terms of x times another function that is purely a function of y. Let me call those two unknown functions capital F. I don't know what this capital F is. I'm trying to find it, times another unknown function that is purely in terms of the variable y. So basically, if I find f and g, capital F and capital G, we are done with the problem. But then the question is how to find this capital F and capital G. Well, the first step is plugging this into the original partial differential equation. So the second derivative of u with respect to x would be equal to, well, g of y would act as a constant because we are taking the partial with respect to x. So the first derivative would be f prime times g, and the second derivative is f double prime of x times g of y. And then similarly, second derivative of u with respect to y is equal to, in this case, f of x is a coefficient times the second derivative of g with respect to y, or g double prime of y. Now we can plug these back into the original PDE. That will give f double prime times g plus f times g double prime equal to 0. Then we could divide left and right by f times g. If we divide left by f times g, we will have f double prime g over f times g plus f times g double prime over f times g equal to 0. Now, g and g for the first fraction and f for the second fraction cancels. So we ended up getting f double prime over f plus g double prime over g equals to 0. Or if we rearrange it, it is equivalent to f double prime over f equals to negative g double prime over g. But note that f is a function of x and g is a function of y. So the second derivative of f over f is a function of x. And similarly, the ratio of g double prime over g is a pure function of y. It is not a big surprise. But how is this possible that a function of x is equal to another function of y, of course, with the assumption that x and y are two independent variables? It's impossible, right? Unless this ratio is just a constant. In this case, I will call that constant k. We do not know what this constant is, but we are confident that this cannot be a function of x or y, because this ratio is just has x on it and the second one has y on it, and there is no way that those two are equal unless each of these ratios are just a constant value. We will see that these constants are going to be called eigenvalues of this PDE, but for now we will continue. So for these constants, we could have three scenarios. One scenario would be that the k is 0. The second possibility is that the k is a positive number. I call that positive number lambda squared because any number times itself is positive, so it would make sense if I represent the second possibility with k equals lambda squared, which is obviously positive, assuming lambda is not 0. And the third possibility is that the k is a negative number. And any negative number could be expressed as negative lambda squared. So with these three possibilities, we have to find out which one of these three cases are consistent with these Dirichlet boundary conditions. So I would say 95% of the time, the boundary conditions that are 0 are the borders that we need to focus to be able to determine which of these three cases would work. If we assume that the k is equal to 0, meaning that f double prime is equal to 0, noting that the f is assumed to be a function of x, when the second derivative of a function is equal to 0, that means that f prime is just a constant like c. And if I integrate one more time, that gives me f of x is equal to cx plus another constant I would call b. Similarly, as the g double prime must be 0 if the k is 0, we will have the same result, that the g double prime being 0 lead into g of y equal to another constant like d times y plus another constant like b prime. So we don't know what the d, c, b, and b prime are, but we do know that they have to be linear functions of x and y, provided that this constant k is equal to 0. Now, to be able to find these constants, we have to focus on boundary conditions. In this case, we have u of 0 comma y equal to 0. Remembering that from separation of variables, we assume that the u is a product of f of x and g of y. I can plug 0 for x, and keeping the y as it is, I will get f of 0, because x is 0, I will get f of 0 times g of y equals to 0 because of this boundary condition. So this is true for all the points along the left hand side of the rectangle. For any y, it doesn't matter if you are talking about this point or this point or this point. Any y between 0 and b should have a 0 u value. So it means that independent of g of y, f of 0 must be equal to 0. And similarly, you can argue that for the right hand side of the rectangle, we will have f of a times g of y equal to 0. So it is true for any point along the right hand side of the rectangle, so it gives me capital F of a equal to 0. So these are the two boundary conditions coming from the left and the right hand side of the rectangle. So if you plug these two boundary conditions back into what we found for f, basically plugging x equals 0, that gives me b, and b has to be equal to 0. And if you plug x equals a, that gives us ca plus 0 equal to 0. So it gives me c times a equals to 0. We know that a is not 0. That is literally the length of the rectangle. So that means that the c must be equal to 0. But c and b equal to 0 gives me f of x equal to 0. And when f of x is equal to 0, it means that the u of x comma y equals to 0. That is called a trivial solution of this partial differential equation. But I'm not interested in a trivial solution, but non-trivial solution. So it means that for this case, that the k is 0, I ended up getting trivial solution, meaning u of x comma y is equal to 0. So I will just pass this and we will go over the second scenario and the third scenario. Let's talk about the second scenario. If the second scenario is true, meaning k is equal to lambda squared, we can do the same process. It's a review from ordinary differential equations. So you have f double prime over f equals to lambda squared, and then you can cross multiply. That gives us f a double prime minus lambda squared times f equal to 0, and then we can solve this ordinary differential equation because capital F is a function of x only, so it's an ODE with constant coefficients of 1 and minus lambda squared. It will have the characteristic equation in the form of r squared, because this is the second derivative, minus lambda squared times, there is no derivative here, so there will be no r here, equal to 0. So this gives us r equals plus or minus lambda, and thus the solution to this ordinary differential equation, capital F of x, would equal to a constant like c1 times exponential of the roots of this characteristic equation, positive lambda x plus another coefficient like c2 times exponential of negative lambda times x, because the second root is negative lambda. Again, we will focus on these two boundary conditions, that f of 0 equals to 0 and f of a equals to 0. So if you plug these two boundary conditions, basically what I mean is plug x equals 0, that gives us c1 e to the 0, which is 1, plus c2 e to the negative 0, which is still 1. So it becomes c1 plus c2 equals to, well, capital F of 0 is 0. So this would be 0. And the second boundary condition is capital F of A equal to 0. So if you plug x equals A, that gives C1 e to the lambda A plus C2 e to the negative lambda A equal to 0. We are dealing with two linearly independent equations. They are linear equations. So the only way that we can solve for C1 and C2 that are non-zero is that first I can solve C1 in terms of C2. The first equation gives me C1 equals to negative C2. Now we can plug it into the second equation. Wherever you see C1, you can plug negative C2. So it gives negative C2 e to the lambda A, positive C2 e to the negative lambda A equal to 0. Now we can factor from C2, and that gives e to the negative lambda A minus e to the lambda A equal to 0. If C2 is 0, automatically C1 becomes 0, and again we will end up getting trivial solution, which is boring, but we are looking for non-trivial solutions. So the only way that this gives me non-trivial solution is that this parenthesis equal to 0, meaning e to the negative lambda A becomes equal to e to the lambda A. But if you take the natural log from left and right, this gives me negative lambda A should equal to lambda A. And knowing that A is the length of the rectangle, I can divide each side by A, so it gives me minus lambda, which is equal to lambda, which is not possible unless lambda equals 0, which we analyzed in the previous scenario. So the second possibility that this so-called constant or eigenvalue becomes positive did not work for this case. So we ended up only having the third possibility, which means that this ratio of f double prime over f, which is minus g double prime over g, become a constant, at which this constant is a negative scalar. In that case, we will have f double prime over f equals to negative lambda squared, and if we cross multiply, this gives f double prime plus lambda squared times f equal to 0. So the characteristic equation becomes, well, this is the second derivative. It becomes r squared plus lambda squared. There is no derivative here, equal to 0. So r is equal to plus or minus lambda times imaginary number I. And we know from ODE that if r is an imaginary number, capital F of x would be in the form of C1 times cosine of the imaginary part, lambda x, plus C2 times sine of lambda x. Again, if you recall from the boundary conditions of the left and right, f of 0 and f of a have to be equal to 0 due to the Dirichlet boundary conditions. So we can plug x equal to 0 because this is x, and we have to get 0. So if I plug x equal to 0 into this capital F, it becomes C1 times cosine of 0 because I'm plugging x equal to 0, plus C2 times sine of 0, and we know sine of 0 is 0, so that would disappear, and we will end up getting C1 equal to 0. So the first term is cancelled because C1 is equal to 0. The second boundary condition is that the capital F of A is also equal to 0. So if I plug x equals to A, that gives me C2 sine of lambda times A equal to 0. And as we know that the C1 is 0, the only way that this product between C2 and sine of lambda A becomes 0 is that the sine becomes 0. Because if C2 is 0 and C1 is 0, again we ended up getting the trivial solution. but we are looking for non-trivial. So sine of lambda a must be equal to 0. And the only way that the sine of an angle in radians becomes 0 is that that angle becomes an integer product of pi, meaning n times pi, in which n is 1, 2, 3, positive and negative. Okay. Of course, 0 is another candidate, but we have already analyzed lambda or k equal to 0 in the first scenario, so I did not include 0 for n. And if we isolate the lambda or eigenvalues, we have more than one constant that would work here. So if I isolate the lambda, that would equal to n pi over a, in which n are all integer numbers, non-zero. And as we have more than one, I would put a subscript n, and these are called eigenvalues of this partial differential equation. Now that we found lambda n, for each of these lambdas we have a corresponding capital F. So from this time on, I will include a subscript for the function capital F. So capital F of n, which is a function of x, is equal to, well, it was c2 sine of lambda x. So this c for now doesn't matter. I will leave it with a cn times sine of lambda n times x. So we found the format of this capital F. Now we have to do similar to find capital G. Now let's recall what the ratio was for the G. So we had negative capital G double prime over capital G equals to k, and k was negative lambda squared. So if we solve the same thing for G, we have G double prime of y over G with a negative here equals to k, which is negative lambda squared. So the double negatives cancel. If we isolate and cross multiply, this gives G double prime minus lambda squared times capital G equal to 0. And if we solve for characteristic equation, it gives r equals plus or minus lambda. So capital G of y is equal to a constant like b1 times exponential of lambda times y, because the variable is y, plus b2 times exponential of negative lambda times y, and this would be g of y. Now, like I said, we have more than one eigenvalue. So from this time on, I will put a subscript for the function g capital N of y equals to a constant like b1, but I will put an n next to it. Again, we don't know these coefficients, we have to find them, times exponential of lambda n times y plus b2n times exponential of negative lambda n times y. So we are almost there, except that these coefficients are what we have to find. Again, I'm reminding you that we've already found the lambda n's, so there is no problem with the lambda n's. They are not unknowns. X and y are the independent variables, so all we have to do is to somehow solve for b1n's, b2n's, or cn's. But before we solve for those coefficients, let's just go back and, have a quick reminder that what was the u in the first place? The u is the unknown function that we wish to find, and u is a product of f and g. So it means that u of x and y is the product of this f and g, but we have more than one f and g. And since the PDE Laplace equation is a linear operator, any linear combination of fn times gn will still be a solution. And that's why we will have a summation over all the n's. Before further expansion of this series, let's work on this capital Gn function. I can play with the algebra and write this b1n in the form of b1n minus b2n over 2 plus b1n plus b2n over 2, right? Because b2n and minus b2n cancel each other, and b1n plus b1n becomes 2b1n over 2 becomes the original b1n. So I played a little bit algebra. You will see shortly why I'm changing this in this format. And for similar second term, b2n, I can write it in the form of b2n minus b1n over 2 plus b2n plus b1n over 2 quantity times exponential of negative lambda n times y. Now we can FOIL this by exponential of lambda n, and if you notice, this blue term is repeating. So I can factor from b1n plus b2n over 2, basically the average of the two coefficients b1n and b2n. So if I FOIL them here, I will end up getting b1n plus b2n over 2 times exponential of lambda n y plus exponential of negative lambda n y. And similarly for these two terms, they are exactly the same, except one is the negative of the other. So if I factor from b1n minus b2n over 2, the exponential of lambda n y is positive, but the second terms become negative because these terms are negative of each other. Why did I do this way? Because we ended up getting some useful functions. 1/2 of exponential of lambda n y plus exponential of negative lambda n y. This is called cosine hyperbolic of lambda n y. And similarly for the second expression, we have 1/2 of the difference of exponential of lambda n y and exponential of negative lambda n y. This is called the sine hyperbolic of lambda n y. This way, I am dealing with some useful hyperbolic functions, and I can call the summation or addition of b1n and b2n with a new coefficient. I can call it, let's say, E1n times cosine hyperbolic of lambda n y, and the second term is the difference between b1n and b2n. Let's call it h sub n of sine hyperbolic of lambda n times y. Now we can plug it into this expanded form. So we have summation from 1 to infinity of f sub n, which is c sub n times sine of lambda n, but we have found the lambda n earlier. It is n pi over a times x, and the second term is g sub ny. We simplified it into this new format, which is e1n times cosine hyperbolic of lambda n, which is n pi over a times y, plus h sub n times sine hyperbolic of lambda n, which is n pi over a times y. Now if we FOIL this expression with the cn times e1n, we will get cn times e1n times cosine hyperbolic of n pi y over a times sine of n pi over a x plus c sub n times h1n sine hyperbolic of n pi y over a times sine of n pi x over a. And n is changing from 1 to infinity. Again, we can call the product of cn and e1n and cn and h1n two new names. I will call them e prime 1n and h prime 1n. They're just names. You can put them any name. It doesn't really matter. So what is going on here? We have two unknowns, e prime 1n and h prime 1n, and we are supposed to solve for these two unknowns. In fact, we have infinitely many n's, and we have two unknowns for each of the n's, so we have 2 times infinity unknowns. So for solving them, we have to use the other two boundary conditions, meaning the value of u at the top and the bottom length of the rectangle are two known functions, lowercase f and lowercase g. So let's apply those two boundary conditions. Let's get started with the bottom one. So we have u of x comma 0 equals to lowercase f. Again, lowercase f is a known function. If we plug, and this is u of x comma y, if we plug y equals to 0 in this expression, wherever you see y, plug 0, it gives me f of x. I'm writing f of x first. Now we will write this sigma n from 1 to infinity of e prime 1n times cosine hyperbolic of 0, because y is 0. Wherever I see y, I will plug 0. But cosine hyperbolic of 0 is 1, so it becomes e prime 1n times sine of n pi x over a. And the second term is plus h prime 1n times sine hyperbolic of 0. Again, because we have y in the sine hyperbolic, and sine hyperbolic of 0 is indeed 0. So the second term will completely vanish. And for the second boundary condition, u of x comma b, it is g of x. So g of x equals to summation n from 1 to infinity times, now let's plug y equals to b. So it gives me e prime 1n times cosine hyperbolic of n pi b over a. And for the second term, h prime 1n times sine hyperbolic of n pi b over a, and both terms have sine, so I will write all of these in parentheses, times sine of n pi x over a. So to solve e prime 1n and h prime 1n, let's first focus on the first equation. To solve the e prime 1n, we need to know three important expansion of a function. First is called Fourier's sine expansion, Fourier's cosine expansion, and the third one is Fourier's complete expansion. These are essential to learn PDE. So if you are not comfortable with expanding a function, feel free to watch my other videos in my channel. But for a sine expansion, it's basically dealing with sine of n pi x over a with some coefficients attached. And basically these coefficients, an, in our case e prime 1n, is just a simple integral. This means that for the first equation, we can easily get e prime 1n, which is equal to 2 over a times integral from 0 to a times this known function f of x times sine of n pi x over a dx. So from this, we are done with finding e prime 1n. Once we find e prime 1n, we will plug it into the second equation for e prime 1n, and the only unknown here is h prime 1n. Similarly, you have a coefficient attached to sine n pi x over a in a series of a known function g of x. So this coefficient, meaning the summation of e prime 1n cosine hyperbolic of n pi b over a, and h prime 1n times sine hyperbolic of n pi b over a, is equal to 2 over a times integral from 0 to a of this time g of x times sine of n pi x over a dx. Once you take this integral, you can subtract it from this term and divide it by sine hyperbolic, and this will easily give you h prime 1n. So we solved h prime 1n and e prime 1n and closed the loop, and we came up with an expression for u as a function of x and y in a series form. Hope you guys enjoyed this video. All I'm asking is you smash the like button and subscribe to my channel for more videos. If you have any questions regarding this video, feel free to ask in the comment section, and I will get back to you as soon as possible. Thank you so much, and see you next time.